So good morning. So my name's Nick. I'm from sunny Scotland, and we've just been talking about brains with Pramon's talk, and now we're going to move on to talk about arms, but not biological arms, technology arms, chips, because we are very excited at the moment in EPCC because we've got a shiny new system, but our system is very special, we think, because it's full of Marvell ThunderX ARM chips. And the idea of this is really a development system whereby we can look at the technology, we can explore the technology and the ecosystem, and really understand and further develop this and its role in the whole HPC arena. So our system is 64 nodes, it's just over 4,000 cores in total, and it's part of a UK-funded effort called Catalyst, which is 3 universities, it's ARM, it's HPE, and it's SUSE. And as I say, the whole idea here is to develop the ARM ecosystem further from the software perspective for HPC. So the idea of where the different MPI implementations fit here is super duper important. And it's really key to understand the different trade-offs and obviously then work with the communities to help improve these things if they need improving. So logging on to our system, we have 3 different MPI implementations installed and good to go. We've got OpenMPI, we've got MVAPICH 2, and we've got HPE's MPT, because it's an HPE machine. Now, if I'm entirely honest, what the users do is they go on there, they module load OpenMPI, and they forget about it. And actually, my angle here, and we'll see this in the talk, is yes, it's quite nuanced, but that's really very naive. Because actually, there's a whole world of different performance characteristics, as I'm sure we all know with these different implementations, and so it's worthwhile taking advantage of all these different things. I mean, actually what's funding my time looking at this and my time here this week is this thing at the top called Accelerat. It's a community of excellence in Europe, and we've got a whole bunch of different codes that we're looking at pushing and further developing in the next 5 to 10 years. And there's all sorts of really advanced things we're doing, like looking at FPGAs, looking at new scientific techniques. But actually, something as simple as module load MVAPICH 2 rather than module load OpenMPI, can we get some nice performance characteristics for these different things? And are we potentially leaving performance on the table as it currently stands? So what I'm going to do in this talk is really frame this with 4 different codes. The first one being HPCG, the benchmark, and then 3 applications that are fairly popular, fairly common on our machines in EPCC, and then using the OSU benchmarks to tease out some of the different communication patterns to help understand some of the different things we're seeing. I will also compare and contrast against some of our other machines. So we've got this x86 machine called Cirrus, completely different architecture, completely different makeup, but it's also got MVAPICH 2 on it with HPE's MPT as well. So quite interesting to see the different performance characteristics on the ARM system. Well, relatively speaking, is that the same on x86 or are there differences? And then also for some context, we've got a Cray as well with its Aries interconnect, just to maybe complete the picture with some of these things. So cracking on, the first thing we looked at with our system Fulhame was HPCG. So who here has heard of HPCG? Okay, so a reasonably good number. For those of you that maybe aren't so much on the benchmarking side of things, this is touted as a replacement to maybe a little bit controversial, but certainly as a complement to Limpac that we've relied on for so many years. And in addition to the computational side of things, we've got the memory in this benchmark and also the communication. And actually, these researchers from Warwick University a few years ago did some detailed profiling, and they found that as you push this out, a lot of your runtime is spent on the communication, and out of this, a lot is in the collectives, which is effectively an all reduce. So what we're doing here is we're running the benchmark with this specific problem size, and what ARM have done is they've taken the reference benchmark and they've optimized it for their architecture, for their compiler. So this is the first version we ran with a different number of nodes, comparing the performance we get with MVAPICH on Fulhame, our ARM system, against OpenMPI. And what you can see is the performance is very close, but OpenMPI, I'm afraid, DK and the rest of your group, is slightly winning as it stands with this. And what the benchmark also does is it generates a whole load of information about the communications and some of the performance of this. So for instance, what I thought was quite interesting with the reduction is it gives us an average and then a minimum and a maximum. And what we can see here is MVAPICH is doing pretty well until it hits about 16 nodes, about 1,000 cores, and then suddenly it shoots right up in terms of the latency or the overall runtime for that communication. And we sort of see that here. You know, this is quite close, this is quite close, but we hit 16 nodes and suddenly the difference between them increases quite dramatically.
That can be fixed with tuning.
Yeah, I'm sure, absolutely, 100%. And, you know, what I'm coming at here, and you're absolutely right, this is MVAPICH 2, not MVAPICH 2X, and, you know, we've taken quite a basic approach to the tuning. Things like, yes, we're using threading here, so we've used some of those options, but then not gone in detail in terms of looking the mapping and the binding that Harry was talking about. And part of the big thing from our perspective is to get some of this feedback from you guys so we can then push this forward. Yep.
What is read and write there? And which read? Which read is that?
Yeah, so these are the point-to-point communications, and that's again coming from the benchmark. And so what this is telling us is when it's doing the reading and the writing, they're both, this is the reading, that's the writing. So they're fairly close here. OpenMPI is slightly ahead, but again, probably with some tuning, we can get that improved. This is the bandwidth, and then that's the writing down here. So this is the optimized benchmark. We've also got the reference benchmark as well. And the reason the reference benchmark is interesting is because what that then brings into play is HPE's MPI implementation on Fulham, because that's only been compiled with GCC, so now we've had to switch over to GCC. But also we can look at this other system, the Cirrus system, and its GCC, and then MVAPICH versus MPT there. Now, you can't make direct comparisons, but we can look at the different things relatively and see if there's any performance properties or patterns here. Now, I want to say a few things about this. The first thing is, I think this is an anomaly, and it comes exactly what you were saying. This needs some further tuning, because this is way, way off this figure and this figure, and with the optimized benchmark, we're simply not seeing that. So I'm pretty sure with this, working with the team here, we can easily get these numbers up and bring them up to close up here. But I thought it was very interesting, moving from the optimized benchmark to the reference benchmark, suddenly we see this massive drop in the performance from MVAPICH. And you know, our sort of further work with ARM is to really understand what the difference is there and why we're seeing that out the box. The other thing to say is you can see the performance difference between the reference version and the optimized version. You know, the optimized version was about 60 gigaflops up to almost 1,000 gigaflops, and it just shows the difference that it makes when you have that knowledge and experience from ARM tuning this thing. But still here on Fulham, OpenMPI is beating MPT. But on Cirrus, it's a completely different story, because on Cirrus, actually, MVAPICH is working really well. And again, this is out the box. There's no specific hardcore configuration or tuning we've put in, but we're getting, you know, much better gigaflops than MPT on that one. So that's working actually really nicely there out the box for us. What I thought was really interesting on Cirrus, on our x86 system, is when I looked at the numbers at the benchmark reports, what we found with MPT is for the all reduction, the difference between the minimum and the maximum was very, very small, very, very small range. Whereas with MVAPICH, the range was much, much bigger. The minimums were way smaller. The minimum time was way smaller than MPT, which is great, but the maximum time was way greater. And it's just calculating the mean here. So I think it's sort of polluting this average. And if they took the median, it would be much lower down. And I think actually what's helping here is, if we were to look at the median, the fact that a lot of these all reductions are much smaller than MPTs is making an impact there. But I thought that was quite an interesting difference in terms of the profile we get from that performance. Now, what I then did, just to explore this a bit further, is looked at the OSU benchmarks and specifically the all reduction performance. And I think it's fair to say on this, it's the MVAPICH is on both sides of it. So on x86, it's working really, really well with the default settings. It's actually the best in terms of comparing it against MPT. It's better. Whereas on our ARM system, the latency is the highest. And exactly as you're saying, I'm sure we can then use some configuration to pull this down. And it would be fascinating to understand the differences in your heuristics that determine the default configurations, to understand why it works so well on x86 by default and not so much on the Fulhame system.
Because it has a, like as I indicated yesterday, we detect architecture.
Yeah.
Detect all the components. So I think this is not being detected properly.
Yeah.
It is a new machine.
Absolutely.
It's not detecting it, so it is using some default fallback algorithms which are not.
Yeah. And that's one of the reasons for this, because then working with you guys, hopefully we can sort of develop the software ecosystem to bring this down. And then very, very similar over 16 nodes. What I found quite interesting here is MPT, it's actually really nasty on Cirrus. You can see it's all this bouncing up and down, whereas MVAPICH on Cirrus on our x86 system is just really nice. It's much, much better. But again, a similar sort of pattern with the all reduce on Fulhame. So that's the HPCG side of things. The next thing we moved on to then was a code called OpenSBLI, and this is a Python code that then generates C that will then call into something called OPS, which abstracts the actual communication layer. And this is quite a common benchmark people use with this, and with strong scaling here, and it contains a mixture of point-to-point communications and collectives. Now, one of the challenges we've got on Fulhame at the moment is that MPT, HPE's implementation, isn't working so well with C++. So you'll only see results for OpenMPI and for MVAPICH. And what was actually quite interesting for us, and for all these things, is initially I did all these runs, and initially MPICH on Fulhame was just wiping the floor with OpenMPI. And that's this default OpenMPI here, where higher being better, and MVAPICH that. And actually what it took was some back and forth with John's team at ARM, and they realized that, out the box, what OpenMPI is doing on Fulhame is it's configuring UCX wrongly. So it's actually not making the best use of that interface, and they figured out the correct configuration to give it, and then by doing that, we could boost its performance up like so. And then all the numbers I'm reporting in this talk are for that modified configuration. But I thought it was really, really interesting, the fact that we got so bad performance from OpenMPI out the box, and if I'm honest, as an applications guy, I would just go in, compile it, and run it. I wouldn't necessarily think about all those different lower level configurations. Whereas MVAPICH, actually out the box by default, is working much better. So it is making some good choices around the interfaces, etc., but I'm sure then there's a bit further we can do to push this up. We did quite a bit of work looking at the different point-to-point aspects. And again, on x86, MVAPICH is working really, really nicely. Again, on our ARM system, I think we need to tune it a bit more. And a question for Harry is, we see this big leap here at about 16.384 message size. And I was wondering if that's because the setting between the eager and rendezvous protocol is maybe not optimal for the system. Because that looked quite similar to something you were showing a couple of days ago. So I think we can probably sort of bring that down further on that. What I was quite surprised at, and maybe I shouldn't be because we've had it for many years, our Cray system is really optimized for large messages, it seems. The actual performance we're getting on our Cray is pretty bad for small messages, but then bringing out onto large messages, it's much better. And then over here, this is MVAPICH on our x86 system, and also OpenMPI on Fulhame as well. So that's the internode latency. We also did intra-node latency, and a similar sort of pattern here. One thing I thought was quite interesting is both versions of MVAPICH, so MVAPICH on our ARM system and also MVAPICH on our x86 system, both show this slight jump here, and I was wondering if there's some sort of I don't know, protocol change, or it's using some different mechanism inside the kernel to send the messages internally for that, potentially. And again, maybe that's a message size thing that would configure that. So I thought that was fairly interesting. So these are all log scales. We then looked at the bidirectional bandwidth, and this is just a linear scale. And what you're seeing here, again, a very similar picture with the Cray. It's real bad, actually, for small message sizes in compared with everything else, but then works much better with big,
So going back to the internode performance, what is the raw bandwidth that the interconnect offers? So how much does the Cray Aries offer versus the interconnects on Cirrus and the other systems?
So I'd need to look up the Cray figures. For the Fulhame system, we're 25 gigabits per second, and for the Cirrus system, we're 54 gigabits per second. So the Cirrus system is more advanced from that perspective. But I would need to look up the Cray figures. So this is the bidirectional bandwidth. And actually, I think exactly what you're just saying, Harry, we can see these differences here because this up here is our Cirrus x86 system, and this one here is our Fulhame system. So potentially that's just the difference in the InfiniBand sort of raw bandwidth it's generating there. And they're converging as they're going up, but again, OpenMPI is giving us better bandwidth at these smaller message sizes. But again, I think with some tuning, we can probably bring these things together. Whereas on x86, MVAPICH is working really nicely. And then just lastly, for this bidirectional bandwidth, on the intranode side of things, this is the picture. And there's something funny going on with HPE's implementation of MPI, because both on Fulhame and also on our x86 system, they track each other like this very closely and then go up actually really pretty high up here, higher than any other MPI implementation on Fulhame. So clearly there's a similar algorithm that they're using to potentially switch between different techniques to communicate the data within the node. So we've talked about two of our applications so far, HPCG, OpenSPLI, and to some extent it's 2-0 to OpenMPI on the Fulhame system, although with the big caveat it's very close, and I think we could certainly change this with some further tuning. But this thing changes now actually with this code that we developed with the Met Office a few years ago that does atmospheric modelling. So things like looking at fog and allowing them to explore that phenomenon in very high resolution. And the reason that this is interesting is because this is the performance we get with this code when we scale it. These are the performance of all the individual bits and pieces apart from the Fourier transform, which absolutely kills us. It's this all-to-all which is just killing our scaling and killing our performance. And so if we can use an MPI library that can help optimize this, that's a massive win. And just in case people aren't so familiar, we're doing a 2D pencil decomposition where we have to do this all-to-all to switch between these different decompositions of the data as we do forward and backwards Fourier transforms. Yep.
So I'm assuming these are like large message all-to-alls happening?
Yeah.
And this is not a global order, it's a row-wise and a column-wise.
Yeah, it's sort of in a slice. Yeah, absolutely. And what's really interesting here, is there
any support to overlap the all-to-alls with some compute, or is it?
Not currently, no. No, so it's a fairly simple implementation. And the reason for that is when we implemented it, the scientists told us they'd never really use it. And then 5 years down the line, it's one of the main things they rely on. But actually, the reason this is really interesting is on Fulhame, it's a completely different picture. MVAPICH is providing us with some massive performance benefits against the other MPI implementations. And, with the previous things, it was very, very close. And actually, really here, it's not. We're significantly faster with MVAPICH than with OpenMPI and MPT on Fulhame. And this is the overall runtime of one of our test cases, which is very heavily FFT dominated. And what I've done here is just split out the timing of the FFTs for that use case. And what you can see is absolutely MVAPICH is spending much less time in the communication for the FFTs than the other technologies. And when we look at the OSU benchmarks, I think actually it's fairly obvious the reason why. Because again, this is the log scale, and on Fulhame, OpenMPI, MPT, the latency is just way, way higher than MVAPICH on Fulhame, and also MVAPICH on the x86 system as well. So clearly you guys are doing something really nice here with the all-to-all and making some good choices, because it's working much better than the other MPI implementations on the machine. And actually this is the one case where it's very similar tracking the performance of MVAPICH on x86. So clearly the algorithm I guess you're choosing is a very similar algorithm. So I thought that was really interesting because it wipes the floor with the other implementations there. And then just drawing this to a close, the last thing we looked at was growmax. So a really popular, well-known code. We've used this to benchmark a whole bunch of different systems. Very common in biology, but also used for other things as well, like material science. So we're using one of the common benchmarks taken from the Biosim website, and we're strong scaling this. And what we're doing here is higher performance is better. And it's pretty close, but actually I think pretty much MVAPICH is beating OpenMPI on the Fulhame system. So for instance, that compared with that, that compared with that, that compared with that. But it's fairly close in terms of the performance profile we're getting. And I think out of all the different applications, this is the one that has the diversity of the communications inside it that some of these other things don't quite have. So maybe this is quite a good view from quite a wide perspective of what we are getting currently out the box, if you like, with these different things. And also, you know, MVAPICH on Cirrus rather than MPT, again, that's showing a performance benefit as well. Now, we've got to be super careful here because on our Fulhame system, per node, we've got 64 cores, whereas on our x86 system, per node, we've only got 36 cores. So how we do the comparison between one system and the other, you do have to be careful, but the Fulhame system, the ARM system, is outperforming the x86 system with this in this situation. Whether you think that's a fair comparison or not, I'm not entirely sure. I'm convinced myself. But I thought an interesting perspective to take on this. And then this very last thing I wanted to talk about is we just did some runs in the past couple of days looking at the single-sided MPI performance. And I put this in because I thought it was quite interesting, some of the patterns of these different curves. So PSCW, very similar to the fences as well on the active target synchronization. We're seeing OpenMPI on the Fulhame system providing, so this is bandwidth, better bandwidth than MVAPICH. And on Cirrus, MVAPICH is going really well until this specific message size and then drops quite considerably. Again, I wonder if it's sort of a protocol change or something.
Is this intranode or internode?
This is internode. This is, yeah.
Okay. Probably protocol change. Weird. We'll take a look at it. Thank you.
Yeah, and then with passive target synchronization with the lock, what I thought was really interesting is on the Fulhame system, up until this point, MVAPICH is performing much better than OpenMPI. You know, in terms of bandwidth, MVAPICH is there on Fulhame and OpenMPI is down here. But then suddenly it goes boom and drops straight down and then tracks quite a similar curve. So again, I suspect something interesting is happening there that's causing that. And we don't see this with MVAPICH on Cirrus, and that's performing.
Could you please let me know which version of MVAPICH you were using here?
So 232.
232, okay.
Yeah. So we've got all the raw numbers and stuff, and we can certainly send those on. Yeah. But I thought that was just quite interesting to see, just these sort of little anomalies, really to understand a good chance being from our perspective if we configured it differently, but also whether there's any different.
We'll take a look at it. Thank you.
So thank you very much for listening. I think it's probably an unfair scoreboard up here. I'm sort of calling it 2-2, but I say it's unfair because with Monk, with where FFTs were dominant, MVAPICH was just so much better than the other communication libraries, whereas with the other applications and benchmarks, it was much closer. And I'm pretty convinced going forwards, looking at MVAPICH X, we can start to really pull ahead with the performance, and again, some of the different options as well that we've got. But from our perspective, at least we've got a baseline, at least we've got a foundation where we can now talk about these numbers with some sense and actually really understand where we are with the technology. Something really sort of that I didn't expect sort of from a left field that came out with this was MVAPICH's Cirrus is really good. On our x86 system, this is what we should be using. And it's not even on there as a module. I had to install it, compile it, and run it. And so now I'm saying to people, don't use MPT, use MVAPICH, or give it a go at least, because actually this is beneficial. And so that's something I wasn't really expecting, but sort of a benefit from looking at this and from this work. So thank you very much for listening. I will not steal you from your coffee break any further, but if you've got any questions, feel free to shout out.
So let's have a speaker.